orals and 3 short oral spotlights. And we are going to start with Maurice Weber. The title of his talk is Observer-Dependent Lossy Image Compression. We will have 12 minutes for the talk and 3 minutes for the discussion. Please feel free to post your questions in the Discord channel. Thank you. Maurice, you can start.
Thank you. Let me share my screen. Okay, yeah, I'm Maurice. I'm presenting to you our paper, Observer-Dependent Lossy Image Compression. So why do we look at image compression? Nowadays, there's billions of and trillions of images on the internet. Billions get uploaded each and every day. So if we have better compression, then of course this saves a lot of bandwidth and storage. So, and in compression, typically there's, there's 2 paradigms to how we can achieve compression. So there's lossy image compression and lossless image compression. In lossy image compression, which is the type of compression that we look at, one allows for an error in reconstruction. So we don't need to have the compressed image look exactly the same as the original one. And this results typically in higher compression rates compared to lossless image compression. Because in lossless image compression, one wants to achieve that the compressed image is exactly the same as the original one. Yeah, so now in our title, we have the term observer dependent. Now, what does observer mean? We define an observer to be a downstream task that uses the compressed image in some sense. And in our work, we specifically look at the human observer, at humans looking at images, and at classifiers looking at images, so classifiers classifying images. Now, why is that? It's because there's an emerging trend that we have an increasingly diverse set of observers that look at images, that consume images in one way or the other. And for each of those different types of observers, the term quality compression quality can have a different meaning. So for example, if we compress images for humans, then the goal is typically that we want the compressed image to remain visually pleasing to look at. So the term quality here really means similarity. We want the compressed image to be as similar as possible to the original image. Whereas if the observer is a classifier, then the goal is a rather different one. We want to describe what object an image contains. So a classifier wants to assign the right label to an image. And here the term quality means rather that we want to have an accurate classifier. So we ask in this paper whether we can optimize lossy compression dependent on the observer. So can we exploit the differences in those different tasks such that we can improve lossy image compression? And it turns out that we can do that. So let me give you a brief overview. We build on neural image compression, and I will then show you our approach to how we achieve observer-dependent compression, and give you the results that we have. So neural image compression. In neural image compression, we have an encoder and a decoder, and they're parameterized as neural networks. So what we do is we learn an encoder which maps input images into a latent space, which gets then quantized with a quantizer and decoded such that we reconstruct the image. And the compression goal, so the observer of the image is encoded in the loss function during training. Yes, and as a compression architecture, there's many ways to achieve that. We use RNN-based compression, which is an RNN-based compression. There's, for example, also it's also possible to use autoencoders for compression or other methods, but we stick to RNN-based compression. And now, as I said, the observer is encoded in the loss function of the training of the compression algorithm, and the state of the art is typically that we have human-oriented compression. So people typically focused on the human observer, And one way to do that is to choose MSSIM. This is one of the most widely used similarity metrics, which mimics or which approximates human perception. And our approach to classification-oriented compression is that we use an L2 distance in the feature space of a VGG network, which was trained for ImageNet classification. And if we have a scenario where we have both human observers and classifiers, then we use the convex combination between the two losses, and thereby we can manage the trade-off between human optimized compression and classification optimized compression. So to design the feature reconstruction loss requires a bit of thinking, because different layers in the VGG network have different semantic meanings. So we need to figure out which layers do we use in our loss function. And with the goal is always that we have a compression system which produces images that generalize across different classification architectures. So we use VGG loss to train the compression network, but we want to have the compressed images to also be classifiable, let's say by other architectures such as DenseNet and ResNet. And it turned out that using one of the first layers and one of the last layers in the feature reconstruction loss leads to the best performance across different classifiers. So for example, here for DenseNet and ResNet, those plots show the validation accuracy on ImageNet against the compression rate. So the higher up the curve is, the better. And we see that the black curve is the best. And this is the curve where compression has been trained with a feature reconstruction loss based on a first and on a last layer in the VGG network. So, and this is a visual example that shows the difference in compression performance, let's say. So on the top row, we have the original image and a BPG compressed image. This is a traditional, an engineered codec. And on the bottom row, we have RNN compression. So on the left side, we have the human favorable loss when we trained compression with multi-scale structural similarity. And on the right-hand side, we have RNN trained with classification friendly loss. So we see that, for example, the leash is in the classification favorable compression is red, whereas in reality it's brown. But this doesn't really matter for classification in this sense, because yeah, so we also have we have checkerboard artifacts, which also doesn't harm classification accuracy, as we will see in the plots. Yes. So if we look at the ImageNet classification accuracy with different classifiers, we see that. So again, this is ImageNet. So each plot shows the accuracy of a different classifier evaluated on ImageNet. And on the x-axis, we have the compression rate. So as we go to the right, we have less compression. And as we go to the left, we have a higher compression rate. And we again see here that the black curve is on top. So this means that the classification optimized compression really is able to maintain accuracy quite well compared to human optimized compression methods. So for example, the gray curve shows RNN compression trained with multi-scale structural similarity, so with the human optimized loss, and other methods also are outperformed by classification optimized compression. So the takeaway is that with optimizing compression for classification, we can improve classification accuracy. But of course, the question is, does this hurt perceived quality, human perceived quality? And the answer to this is yes. We can see this in these plots here. We have on the y-axis the MSSIM index, which shows that the black curve now is among the worst in these examples, but still competitive to JPEG actually. But it shows that if we optimize compression for classification, then this does hurt human perceived quality, but it's still competitive to JPEG. If, on the other hand, we optimize RNN compression with the human favorable loss, then this results in a compression system which is competitive with the better methods. And finally, to look at the trade-off, I introduced this parameter alpha with which we can balance or trade off the observer. So as we increase alpha, we see in those plots that the blue curve typically is increasing, which means that as we increase alpha, the preserved validation accuracy is increasing. Whereas at the same time, the gray curve is decreasing, which means that the multi-scale structural similarity index becomes worse as we increase alpha, unless we want more classification-friendly compression. And additionally, we see that if we decrease the compression or increase the bitrate, then this trade-off is less pronounced. So in conclusion, we have seen that we have looked at the human observer and classifiers in context of compression, and we asked whether we can optimize lossy compression depending on those observers. And we found that yes, we can do that, and we can, by using this type of loss functions to train neural image compression, we can increase classification accuracy and found a way to trade off the two observers against each other. So thank you a lot, and I'm open for questions now.
Thank you, Maurice, for a very nice presentation. Just as a reminder, if anyone wants to ask questions, please go to the Discord channel. You can find the link to the current Discord channel from the program on the website. I have one question. So you talked about human favorable loss and the classification favorable loss, and I was wondering, to measure the human favorable loss, have you done user studies, experiments on humans?
No, we have not done experiments on humans.
How do you measure, so how do you define that loss?
Multi-scale structural similarity, that's a distance measure which is inspired by the human cortex. So it looks at an image at different resolutions essentially.
Okay.
And yeah.
I see. Yeah, it seems we got this exact same question from Discord.
Okay.
Okay, so structural similarity metric is used for the human.
Yeah, exactly. Yeah, multi-scale structural similarity.
Okay.
Yeah.
Okay, thank you. Are there any other questions from the audience? Okay. This seems not to be the case. We can move to the next speaker. Yifei Zhang is going to present, and the title of his talk is Adversarial Synthesis of Human Pose from Text. Yifei, you can connect with your video. Thank you.
Yep. Yeah. So
Is setting up. You can ask questions from the Discord channel.
Back.
Okay, so now start, or?
Yes, please. You have 12 minutes and then 3 minutes of questions.
Yeah, it's time. Okay. Hello everyone. My name is Yifei. And the work I'm presenting today focuses on synthesis of the human pose from human-level text descriptions. And my supervisors are Professor Dr. Gall and Rania and Julian from the University of Bonn. And this is also the main content of my master thesis. So our goal is to synthesize versatile human poses from text. Given a human level text description, we want to see if we can generate a semantically consistent human pose. Here is an illustration. This is a text description. Give this to a generative model, for example, a GAN, and the model can generate realistic and consistent pose like this. And this is what we want to achieve. Our model may have some applications. For example, it can be used in animating avatars based on human-level text descriptions. So animating avatars, something like this. Yeah, animating avatar. And also, recent image synthesis works like this one still generate images with deformed humans. And we think that the poses generated by our model may be helpful for synthesizing images with realistic human poses. And also, it can be used in retrieving images with thematically related poses. For example, if we want to retrieve images in which a person is playing tennis outside on the tennis court, we can first generate some poses from this sentence and use these poses to retrieve the correct images. So in our approach, the text features are represented using a fast text encoder. So a text T and the fast text encoder phi computes the word embeddings and encodes the text into vector H. And for the post-joint features, we use 2D heat maps to represent them. In each heat map, the joint is modeled by a Gaussian distribution centered at the joint coordinate. Compared to directly using coordinate, heat maps allow implementation based on convolutional networks. And also, it's more convenient to represent invisible joints by just setting the values to 0. So here is a pose with 17 joints, and it will be represented by 17 heat maps like this. And our model is based on Wasserstein generative adversarial network, which consists of a generator network G and a critic network D. G generates heat maps from the noise conditioned on the encoded text, and D discriminates real or generated heat maps, also conditioned on the text. And during the training, both networks are trained simultaneously together. The Wasserstein GAN we use different from the vanilla GAN. In the vanilla GAN, this is the min-max objective of the vanilla GAN. Here, X is a real sample, and Z is the input noise. G is the generated sample. This is related to the Yazan-Shannon divergence between real and generated sample distributions. And a problem with Yazan-Shannon divergence is that the loss is not always differentiable, which can result in training instability. And on the other hand, Wasserstein GAN uses another min-max objective, like this one, and it is related to the Earth movers distance between the two distributions. And here the loss is almost always differentiable, so the training stability is better. In our model, the objective of D is to maximize the distance between real heat maps and generated heat maps or heat maps with mismatching text. This is the loss term of D. It deals with two types of errors. The first term corresponds to unrealistic poses, and the second term corresponds to mismatching poses and text. So in WGAN, as constraints that D here must be Lipschitz continuous. So we also need another Lipschitz penalty term like this one, which limit the norm of the gradient of D to 1. And here x hat is sampled randomly along the line between a pair of real and generated heat maps. So the total loss combines the loss term and the penalty term with the coefficient lambda. And for G, the object is the opposite, minimizing the distance between real and generated heat maps. And this is the loss term we use for G. Here we add an extra term. This term adds more training samples near the manifold by interpolating between two randomly sampled text encodings, H1 and H2. This is the network architecture of the generator. So the text encoding is concatenated to the noise, and after some layers of transposed convolution, we get a set of heat maps in the end. And for the critic, the input is the heat maps. And after layers of convolution, the text encoding is also inserted into the network, and then the final output is a single number. So in our experiment, we use the COCO dataset. This dataset contains a lot of images of everyday things, and the human poses in these images are very versatile. And the dataset also have annotations, including key points coordinates and the human level text descriptions of the scene. Here are some example images from the dataset, everyday things, and this is an image with annotations. We can use these key point annotations to extract a human pose, and the image also have a text description like this. So in our experiment, we compare our model with two other baseline models. The first baseline uses joint coordinates instead of heat maps. So we call it regression-based model. And in this model, fully connected networks are used instead of convolutional network. And the second baseline model uses vanilla GAN instead of Wasserstein GAN. So Jensen-Shannon divergence is used instead of Earth movers distance. Yeah, so here are some qualitative results of our model. The first line are some random ground truth poses from the validation set with text, and below are generated poses from our model. And so now we can see that the text encodings are indeed effectively guiding the synthesis of the poses, such that the generated poses resemble the real poses and can reflect the text. In particular, for distinct actions like throwing in this column and working on computer in this column, and also surfboarding in this column. So these are comparisons with the baseline models. We can see that the regression-based models generate less realistic poses than our heat map-based models. And for the vanilla GAN, the training is unstable. Here, mode collapse occurs such that there are many repetitions and unrealistic poses generated. And also, in addition to the qualitative results, we also came up with some quantitative measures for additional evaluation. And our model also performed better when evaluating it quantitatively. And we also do the interpolation test on our model. So on the left and on the right are the poses generated from the text, and in the middle are poses generated from interpolated text encodings. If the generated poses show smooth transition between the interpolation, we can conclude that the model actually learn a proper distribution instead of just having memorized training samples. So here in our results, the transition is smooth from left to right. And also, it's interesting to see what happens if we give the model only part of the sentence. So these poses are generated from the whole sentence, and then we input each part of the sentence to the network, like a man in blue shirt is playing a tennis game on the court. So here we can see that specific verbs and nouns like playing and tennis here matters more in the synthesis of this post, which is interesting. And we also vary the post subject in the description. Here, these four descriptions are the same except for the subject, and but there is not much difference in the generated poses. So the subject in the text does not matter very much. But although the poses for younger people are slightly smaller. So in conclusion, our work addresses the task of human pose synthesis from text with highly complex poses, and we design an effective model using a conditional Wasserstein that generates poses consistent with text descriptions. And the proposed approach is effective. It outperforms a vanilla GAN and a regression-based approach. Okay, these are the references of our work. And that's all for my presentation. Thank you.
Thank you, Yifei. Very interesting presentation. We have a couple of questions from the audience. So regarding the results that you have shown, do all the activities, so for the qualitative results, do all the shown activities or words that are input to the model appear in the COCO dataset?
So all the words in
the activities that these poses are doing, do they all appear in COCO? Or can your model also show images or poses that it has never seen before about activities that it has never seen?
Those poses are from the validation set, so it's not seen before by the model.
Not the poses, but the activities that the people are doing, like playing guitar or riding a wave on top of a surfboard. Do they all appear in the training set?
Yes, I think most of the normal activities are included in the dataset because the COCO dataset, I think it contains all range of activities. But yeah, in our work, we also try to use our own sentences to try to test the model, and the result is also good. If you feed the model with something like sitting, riding bike, or some everyday activities, it's good for the pose.
Okay, one quick question. Have you tried VAEs instead of GANs? For
No, No, we only try again. From beginning, we use the vanilla again, and the result is not very good. So then we use the Wasserstein again. Then we think the results are satisfactory.
Mm-hmm.
So we only try again model.
Okay, I have one quick question. In your loss function, you were minimizing the distance between a real image and a mismatched text. Have you also tried a real image and a matching text? I remember maybe 11 or so you were showing your loss function.
No.
The previous slide, 10, I think.
Yeah, this for G. Oh no, sorry. This
yes,
one.
this one. So generated heat
so
maps with mismatching text. Have you also tried real heat maps with the matching text?
But the real heat map is matching text is this DXH.
Oh, okay. This
yeah,
is already in the loss
yeah.
function.
These are the ground truth left, and this is the incorrect with mismatching text, and this is the text with generated heat map.
Okay, I see. Okay,
yeah.
Thank you. Let's move to the
Thank
next speaker.
Okay.
Now we have spotlight presentations. The first one is Yazan Farha, and the title of his presentation is Long-Term Anticipation of Activities with Cycle Consistency. Let's please turn off our videos if we are not speakers. And we are going to have 5 minutes of the talk and 2 minutes for questions. Please feel free to enter your questions in the Discord channel. Thank you.
Okay, thanks for the introduction. In this talk, I will present our work for anticipating activities. This is a joint work with Qiuhong, Bernt, Schiele, and Juergen Gall. So let's start by defining the task. What we are given as input is a sequence of observed frames for a person doing some activities. And our goal is to predict what are the possible future activities with their durations. So in this example, the person would add tea bag and then pour water into the cup. This task has many potential applications in robotics to improve human-robot interaction, and also it has applications for anomaly detection. Previous approaches addressing this task followed a two-step approach. In other words, instead of directly predicting the future activities, they first infer the frame-wise labels of the observations, and another model is trained on top of these labels to predict the future activities. These two steps are decoupled, which means that if the first step generates a mistake, this mistake would be propagated in the future predictions. In contrast to these approaches, we propose a framework that directly predicts the future activities from the observations. Furthermore, as we humans can reason about the past given the future, we also enforce cycle consistency by predicting the observed activities from the predicted future activities. Our framework consists of a sequence-to-sequence model based on gated recurrent units that map the sequence of observed frames into a sequence of future activities with their durations. Then to enforce cycle consistency, we use the hidden state of the decoder to predict the observed activities alongside with their durations. Also, as the activities in the observations can serve as a strong signal for anticipation, we combine the encoder with a recognition module. So we first pass the frames into a TCN-based recognition module and apply a segmentation loss as an auxiliary loss before passing the output to the recurrent encoder. We perform ablation analysis on the breakfast dataset. Starting with a sequence-to-sequence model, our model achieves a good performance between 20 to 27% at different observation prediction percentages of the videos. And if we add the recognition module, we get a consistent 1 to 2% improvements. And then if we enforce cycle consistency, we get an additional 1% as well. We can further combine the sequence-to-sequence model with attention mechanism, and this will give an additional boost in performance. So quantitatively, we have seen that cycle consistency gives 1% improvement. Nonetheless, we have seen that in the qualitative results, there are two main effects of this module. So the first effect is that by using cycle consistency, we make sure that the model would predict all the necessary actions. For instance, if we have a video for a person performing, mixing some ingredients to fry pancake, then a model without cycle consistency would predict that the person would pour the mix into the pan and start frying the pancake. Nevertheless, with cycle consistency, the model would recover that you need to pour some oil into the pan before start frying. Also, by enforcing the cycle consistency, we encourage the sequence-to-sequence model to keep all the important information from the observations in the memory. This means that if the model generates some wrong predictions in the intermediate steps, these wrong predictions would not necessarily propagate into the future ones. We tested our model on two datasets, the breakfast dataset and 50 salads. On the breakfast dataset, our model achieved state-of-the-art results with 5 to 8% improvement compared to the previous methods. Nevertheless, on 50 salads, our framework achieved comparable performance. This is mainly because 50 salads, it's much smaller dataset, and end-to-end training tends to overfit. Here we have a qualitative results from the breakfast dataset for a person trying to prepare a cup of milk coffee and chocolate milk. And here we see that after observing the frames, our model generates a sequence of future activities with the starting time and ending time of each activity. In this particular example, our model generates the future activities up to 38 seconds in the future. So to summarize, we propose a framework that directly predicts the future activities from a partially observed video. We also demonstrated that recognition can help anticipation, and we employ it as an additional supervisor signal. We also employ cycle consistency as an additional supervisor signal to anticipate the future activities. Our framework achieved the state-of-the-art results on two datasets, the breakfast dataset and 50 salads. Thank you.
Thank you, Yazan. Very interesting work. I have one question. How long typically are the videos in the datasets that you have?
Yeah, so in these two datasets, we have videos of various length. On breakfast dataset, on average, we have 3.5 minutes. On 50 salads, also the average is the same. However, we have the longest sequence on both datasets up to 10 minutes. So in total, we predict up to 5 minutes in these datasets.
How do you handle the varying length of videos?
So in principle, the recognition module is temporal convolutional one, so there is no problem with the varying length. And then we have a sequence-to-sequence, it's an RNN. So in principle, we can handle videos of varying length, and there is no problem with that. Nonetheless, in the evaluation, we had to stick with this protocol where we evaluate at percentages, not at absolute length. So we do not say the performance at 5 minutes or a performance at 1 minute, but we say the performance if we predict 10% or 20% of the video, something like that.
Okay. We have one question from the audience. What metrics did you use for evaluation?
So the metric that we are using is mean over classes. So this means that we have accuracy for each class separately, and then we average these accuracies. This metric, we use it instead of like frame-wise accuracy, because frame-wise accuracy usually prefer long actions. But if we use mean over classes, we make sure that we have proper evaluation for both long and short action segments.
Mm-hmm. Okay. So for the sake of time, we have to move to the next speaker, but I would invite the audience to stay for the discussion session afterwards. Thank you. Our next speaker is Soumajit Majumder. The title of his talk is Multi-Stage Fusion for One-Click Segmentation. You can start, Majumder.
Sure. Is my screen visible now? Yeah. Okay, so the title of my talk is Multi-Stage Fusion for One-Click Segmentation. This work was done with Ansh and Abhinav, who were working at NUS and under the supervision of our professor, Dr. Yao. So before going into the how and why, let's start with a brief background. So what is semantic segmentation? It essentially answers the what is where question. And what it does is it performs a per pixel classification. For each pixel, it assigns a class label from a set of labels predetermined for the dataset. And state-of-the-art approaches performing semantic segmentation use fully convolutional networks. Instance segmentation goes one up on semantic segmentation, and it also predicts the individual object instances. Different from semantic and instance segmentation, one-click segmentation allows users to select a specific object instance and then get the segmentation mask for that object. So one possible application of this is background blur, commonly seen during mobile photography. For example, you want to blur the background and keep the dog in focus. And for that matter, you place a click on the dog and the rest of the background blurs out. You can also use this application, for example, in Zoom. And how it is done, and with our proposed method, you can see like much crisper edges, which gives you nicer blur basically. So existing approaches, what they do is they take the click and transform it into an image size channel using Gaussian transformation or Euclidean transformation. This is then appended with the 3-channel RGB input, making it a 4-channel input, which is passed through a standard FCN. This can be FCN 8S, this can be DeepLab version 2 or anything. And in the end, we are targeting to get the segmentation mask for the target object. But the issue in existing approaches is that the interaction, the user selection click is only used at the input layer. And then this information is passed through several number of layers of a CNN. And what happens is at the end, this can lead to a weakened influence. So to mitigate that matters, there has been recent approaches which has tried to address this. One approach is using late fusion, where they multiply the feature maps obtained from the convolutional layers with the positive and negative maps, and then they pass it through a new decoder. So this decoder has to be trained from scratch. The issue with this is this can lead to an increase in the number of decoder parameters. One advantage, however, is that it leads to faster updates because you don't have to extract the features for the object each time you add a new click. Another approach doing a multi-stage fusion is this two-stream approach, where they use a dedicated VGG network. But with the use of a new network, you have this issue of slower training because you are limited in your memory on the GPU. So these are the limitations of the existing approaches. So one, we have the heavy computational footprint arising from the retraining of the decoder, and given the fact that the feature maps increase in size by a factor of 2, and then there is the use of an extra network. What we propose is a small, lightweight, late fusion block that can work alongside the main segmentation module. And in the end, we concatenate the features from our late fusion module and the main segmentation backbone, which is the DeepLab version 2, and then we pass it through the prediction head. For our case, we use the pyramid scene parsing module as the prediction head. So this is the architecture of our approach. And we use the AC ResNet because it has more discriminative ability compared to the usual ResNet blocks. And this proposed approach is lightweight, and we do not need to have a separate network to pass the user interaction to the output. So first, we discuss some of the baselines that we have used. So the first, so during training, we use the user click, which is placed at the center of the object. And then we train the FCN to minimize the binary cross entropy loss. In these three approaches, we only use the early fusion module and do not take into consideration the late fusion. And we observe that when we do a multi-stage fusion, it leads to a performance improvement. And we see an overall increase in the average mean intersection over union given a single click. Next, we compare our approach to existing state-of-the-art approaches. So the approaches are divided into 3 categories. One is the classical methods, which are the pre-deep learning era methods, and the next one are the deep learning era methods. And then there is one work on one-click segmentation. We outperformed them on more or less all benchmark data sets. Next, we look at the qualitative improvements that is a byproduct of this multi-stage fusion. In the first row, you see masks that are generated using the baseline model. And in the second row, you see masks that are generated using the multi-stage fusion. And you can observe visible improvements, for example, in the ears of the giraffe, and also that the mask of the bus is more complete in the latter one. And in summary, yeah, we propose a multi-stage fusion, which leads to a better use of the user interaction, which leads to better segmentation mask, and also it also outperforms state-of-the-art approaches. Thank you.
Thank you, Soumajit. So I don't see any questions from the audience at the moment, and we are a little bit over time. So I would suggest to move to the next speaker, and please stay for the discussion afterwards.
Sure.
Thank you. The next speaker is Jovita Lukasik, and the title of her talk is Neural Architecture Performance Prediction Using Graph Neural Networks. You can start, Jovita. We can't hear you yet.
And now?
Yes.
Good. Okay, so thank you for the nice introduction. Okay, so, sorry. Okay, so now, thank you for the nice introduction. I'm going to present the work Neural Architecture Performance Prediction using Graph Neural Networks. Our motivation is the problematic that in neural architecture search, all neural architectures in the search space needed to be evaluated. This leads to long computation times and therefore also to restricted search space. This problematic calls for the need to have an accurate surrogate model at hand, which enables to predict the performances of structurally different and larger architectures. And that's exactly the task in our paper we want to tackle. We want to learn to predict the accuracy of convolutional neural architectures in a supervised way using continuous representation of neural architectures. For that, we use a graph neural network-based model as an encoder to encode the discrete graph search space into a continuous vector space. And we want to answer the following questions. How well can we predict the accuracy from the continuous embedding space in the traditional supervised performance prediction task and also in a zero-shot performance prediction task? Since it's all in a supervised manner, we also need a data set. We chose the NAS Bench 101 benchmark dataset, which is the first public architecture dataset for neural architecture search. It contains around 423,000 unique convolution architectures are trained and evaluated all on the Cypher-10 image classification tests. Furthermore, this benchmark contains cells, therefore it's just a cell space. And in the cell space, we have in total all possible directed acyclic graphs with at most 7 nodes, at most 9 edges, and also 3 different possible labels. Furthermore, matrices as the validation accuracy are given as annotations in our benchmark. We can see also in figure 1 on the right-hand side how these cells looks like, and on the left-hand side how they are stacked together to create the overall network. As already mentioned, we use a graph neural network from the literature to exploit the cell structure. And exactly in figure 2, we can see the 2-step procedure in our graph neural network, where on the left-hand side, we can see how the node levels are upgraded and aggregated. And then these aggregated node attributes are used to generate one single graph embedding by aggregating on the graph level. This graph embedding is then used as the input for a just simple MLP regressor to regress the performance prediction. And as already mentioned, we are interested in the fact of how well can we predict the accuracy from the continuous embedding space in traditional supervised setting, which just means that we split our data set into training, test, and validation set. And we can see in table 1 that our encoder is able to predict the performances in a stable way and also comparing our model to several baselines. The more interesting experiment is actually how well can we predict the accuracy from the continuous embedding space in unseen regions. This task can be furthermore divided into an interpolation and extrapolation task. The interpolation task means that we train our encoder on graphs with length 2, 3, 4, 5, and 7 and test it on unseen graphs with the length of 6. And the extrapolation task is actually that we train our encoder on graphs from the length 2 to 6 and train it on larger architectures with at most length of 7. And we can also see in this experiment that our encoder is very good in predicting the performances correctly and also outperforming the baselines we already have seen in the experiment before. Of course, we also compare our encoder to the most recent state of the art regressor. In this setting, we sample 1,000, 10,000, 100,000 architectures out of the NASBench dataset, train it on these samples and test it on all the others. And also there we can see that our encoder is in line with the regressor from the state-of-the-art regressor and actually is slightly better. And so we can actually say that with kind of a simple GNN encoder regressor, we have a very strong and powerful tool at hand for a surrogate model for performance prediction tasks, especially in the zero-shot performance prediction task, where we have never seen the architectures before, which makes it actually quite nice. Yeah, that's all. Thank you for listening.
Thank you for the presentation. I have one quick question.
Yes.
So the zero-shot task,
Yes.
do I understand correctly that you have architectures with different layers in the beginning, and then you have a type of architecture with a particular number of layers that you have never seen before, and this is what you are predicting?
Exactly, that's what we have in this whole data set. We have at most 7 nodes. So we have in total cells having 2 to 7 nodes, and that's exactly the whole amount in the benchmark data set we're using. And therefore we can split the training, encoder training, just having graphs with a certain amount of length. And therefore we can say that we have never seen the cell space with a length of 7, since all these cells are then stacked together to create the overall architecture. So the architectures just differ with the cell itself. And if we have smaller cells, then we have also smaller architectures, and larger cells, larger architectures, which we've never seen before.
Okay. And there is one question from the audience regarding the hyperparameters. So they say you are predicting the performance of neural networks based on their architecture. How about hyperparameters like learning rate, which have an effect on the performance, right?
Yeah, that is work we did not focus on. We were just focused on the performance prediction itself, just having the cell, like just the directed acyclic graph. We just have one graph, like the topology itself. We never used any hyperparameters information as annotations, but there is work which is doing that or focusing on also predicting hyperparameters, but we especially did not do it because we just wanted to focus on the topology itself without any other annotations.
Mm-hmm. Okay, thank you. Well, more and more questions are coming, but now we actually have to close the session, at least the talks part. We have a discussion now, and the discussion is not going to be recorded. It's not going to be on YouTube, but please feel free to stay in Discord channel and discuss with all the speakers. I would like to ask all the speakers to turn on their videos because so we are at the end of the session, and I would like to thank all of you for all your contributions and for all the nice talks. This basically concludes our session. Thank you. Have a nice evening.
Thank you.
Bye.
Bye.